Welcome back, everybody, to hardwear.io. Our next talk is titled Things Not to Do When Using an IO Memory Management Unit by Ilja and Joseph. Ilja is the Director of Penetration Testing at IO Active, and Joseph is the Principal Security Consultant. They would explain in detail why DMA is not your friend and your hard disk shouldn't be able to read kernel memory and read out keys. Over to you now, Ilja and Joseph.
Cool. Okay, so yeah, our presentation is called Things Not to Do. Hold on. It's called Things Not to Do When Using an IOMMU. Let's see if this works. Yes. Okay. And so it's been by me, Ilja van Sprundel. I am the Director of Penetration Testing at IO Active, and my co-presenter, Joseph Tartaro, who is a Principal Security Consultant, also at IO Active. So what does this talk about and what is it not about? Well, let's first talk about what it's not about. So it's not about bugs in the IOMMU, and it's not about bugs in the platform that supports the IOMMU, so your bootloader OS hypervisor, right? So what is it about? Well, we're going to assume the IOMMU itself works as expected. We're going to assume your platform and its IOMMU drivers work as expected. So this talk is about basically drivers that interact with their hardware and that use platform APIs to program the IOMMU and give it access to certain pieces of memory when it needs to. And in particular, all the things that can go wrong when doing this. So our agenda is basically pretty simple. I'll start off with a very simple history of like what leads up to the IOMMU, and then we'll describe the primary attack surface, and then we'll just dive right into all the cases that can go wrong when using IOMMU from a driver's perspective. And then we'll have a short conclusion at the end, and we'll have a call to action. I think it's important to note that we didn't do this in a vacuum. We are standing on the shoulders of giants. We based ourselves on the work done by many that came before us. Right, so a little bit of history. Way back in the day, when a device wanted to share data with a CPU, it would send it over a bus or PIO or something like that, and it would send it directly to the CPU. And the CPU would then receive it and handle it. And that worked pretty well for a while, but as devices became faster and as they were sending more and more data, this process was really slow and it would tax the CPU. And so a system was devised where basically the CPU would grant the device direct access to memory. And whenever the CPU wanted some kind of data from the device, it would go to the device and say, hey, you know, here's an address, go write your stuff to it and let me know when you're done so I can handle it. And so that's what the device would do, it would write stuff there, it would generate an interrupt or something, and then the whole CPU would wake up and say, okay, let me now go handle that data. And that worked really well, got massive performance boost, and it's still pretty much how things work today. But some issues do come up. So memory grew, and older devices were not able to always deal with that. So for example, old ISA devices, they can only access 24 bits, so the first about 16 megs or so of DRAM. And so if you have a machine that has more than that, which most machines do these days, then that could be a problem. And then the same kind of issue showed up once we had more than 4 gigs of DRAM. And so there's lots of hardware out there that can only access the first 4 gigs of DRAM. And so that became a problem. And so certain solutions were devised. One is to use a bounds buffer, where if somebody wants to share some data, they would create an outlook or something, and then they would go to use an API and say, okay, here, go share this with the device. And then then that would create a second buffer in the low memory and then give it access to the device. Another solution is to basically create special APIs where you say, hey, go map this in low memory. But again, now your driver needs to be aware of this. And so there's a third solution where you can use something called an IOMMU that would remap things. So you would create some allocation in high memory, and you go to IOMMU and say, hey, by the way, just remap this address. Just sort of create an alias but make sure it's in low memory, and so now the device can access it. So those are kind of that's more or less at a high level, sort of in a nutshell, the timeline. And you'll see IOMMUs in various forms and shapes and lots of abstracted APIs around it. So, okay, but an IOMMU could do more than just remapping, right? So as you can see in this picture on the right side, when your host CPU talks to main memory, it goes through a memory management unit. And then when your device talks to main memory, it goes through a similar thing called an IO memory management unit. And most memory units can do this kind of translation, but a lot of them can also have sort of ACLs and lists where a host can program the IOMMU and say, oh, hey, I want to have a piece of DRAM and I want to share it with that particular device. Here's an address and just this length, but don't give it access to anything else, just that buffer. And so the IOMMU effectively sort of becomes a firewall where a device can only access what is explicitly allowed to access by the host. That has interesting properties and allows you to sort of create a trust boundary between devices and DMA that wasn't there before. And people have done this. And so we've sort of outlined 3 specific attack surfaces where an IOMMU can be helpful. So the first one is external ports. So if you have a laptop or a desktop with something like Thunderbolt or PCMCIA, you may want to see it as a trust boundary because someone could just walk up to your machine, plug something in real fast, plug it out, and if they have access to all of DRAM, they can easily compromise your machine. And I mean, someone just walking up to your machine, plug something in, plug something out, generally isn't too suspicious. If you're security folks like us, and you're paranoid, yes, that may be suspicious, but to my mom, for example, that wouldn't be suspicious at all. So that's one place where an IOMMU can help. The second one is when you are trying to make secure devices. So let's say you're a hardware maker and like you make a smart TV or a tablet or some IoT device or something where you want to strictly control the consumer environment for your device. And so the way you do that is you generally create a quote unquote secure device. So you have a root of trust and a chain of trust, and everything that sort of boots is under your control. And so if you have a device somewhere that exposes PCI or DMA, then you may want to secure that too. And so again, you would use an IOMMU for that. And the third case where IOMMUs can be helpful for security reasons is virtualization. So let's say you have a quote unquote secure guest and you want to share some hardware with it, but you don't trust the hardware. You can use an IOMMU for that to basically make sure that the device can't trample all over DRAM for your guest. These are all real cases that are being deployed and used today. And the set of cases just grows every day. And all 3 of them having IOMMU and sort of having correct usage can help mitigate DMA attacks. So this is a slide from a presentation that was done last year on an attack called Thunderclap by some folks at the University of Cambridge. And I wanted to have this particular slide in here because it so succinctly captures what we're going to describe in the next couple of slides. And it basically says that the attacks in the IOMMU attack surface is incredibly rich and complex and nuanced, and is substantially more powerful than attacks by message passing devices such as USB. And that you really kind of more have to look at it like a syscall interface where you have an untrusted user land and a trusted kernel, and there's a bunch of memory that goes back and forth. And that to me just rings so true. And you'll see that reflected in the next couple dozen slides or so. So that's why I wanted to have it on here.
Okay, sorry, I was muted. Yeah, let's quickly go over some of the common cases of IOMMU misuse. So these are based on some of the behaviors we've seen over the last several years of looking at devices that use an IOMMU in some sort of way. And we're going to walk through some real world examples using the Linux and BSD projects, but these issues could likely apply to other things like Windows and OS X, etc. So because of various reasons to communicate with the devices and set up DMA allocations and such, there are abstracted APIs. And the general form would be that you allocate a buffer, you map that memory, you inform the device about the mapping, it will do its behavior, then you will unmap it and free the memory. So here's some pseudocode showcasing that. We allocate 100 bytes, we map it, we'll inform the device of the mapping, it does its thing, then we will unmap it and free. And so that's a very basic general idea of what we're going to be talking about and what you're looking at, though in a lot of environments, there's a lot of environment specific things, so it might be slightly different. But for your understanding of what we're talking about, that's really all you need to know. So these are the categories of common misuse that we've put together. You have the overall conceptual issues, you have a lot of different mapping issues, race conditions, information leaks, parsing issues, and then we have some miscellaneous things left over we want to cover. So starting with legacy drivers, you'll still see these in projects where you have these legacy drivers that simply get a physical address, they'll give it to a device, nothing gets mapped, and if you have an IOMMU turned on today, this is just not functional. It will not work, and they still exist in a project for people who don't have an IOMMU, and just it's too much effort to remove the driver, too much effort to update it. Nobody really cares or not. But even though it's not necessarily functional, there's still some DMA-related attack surface concerns because they still might be using PCI bars, MMIO, or IO ports. So if the driver is querying information from the device, it can still run into issues querying those areas. And then you have overly lax permissions. So like Ilja said earlier, the IOMMU can be thought of as a firewall. So you can go ahead and set up read-only or write-only situations, and that is awesome. You apply the principle of least privilege, and that's the way it should work. And the Linux kernel documentation even hammers on this. They say you're strongly encouraged to specify this as precisely as you possibly can. But unfortunately, as you look at drivers, you'll see a lot of developers just do bidirectional, and they set mappings as read and write for DMA operations, even though it's not actually necessary. And then you have device logic and functionality concerns. So just because you have an IOMMU does not mean that somebody can create a malicious device and a driver and just tell it, hey, I want to map a bunch of physical memory to this device. Like there's nothing you can really do about that. And we see this all the time with poorly written drivers for things like gaming mice and gaming keyboards, where you'll find that there's an ioctl that allows you to just read and write to any physical memory. And in this scenario, if somebody writes code to do that and you load it, that's just the way it works. And unfortunately, there's no real easy fix to that. Maybe there's a way to kind of rethink how this works, but at the moment, that's just how it is, and that's life. So diving into mapping issues, what happens if you have a missing unmap? And this is where you go ahead and have an allocation, you map it, and then eventually that memory back in the allocation goes out of scope, but the mapping still exists. So in those situations, the device still potentially has read-write to those physical pages, but from your perspective, from the driver perspective, it's done. And that's where you'll run into a bunch of use after free scenarios. So the three common cases that we've categorized are just leaked mappings from different behavior, unmappings that are controlled by the device itself, and just unmapping too late with race conditions. So with your leaked mapping, this is where you would go ahead and create a mapping. The device would use the map memory, and then once the driver is done, the buffer eventually just goes out of scope. And this could be that the developer just simply forgot and they just did not do the unmapping, or maybe there's some sort of weird edge case or error corner case that led to the behavior where the unmapping just did not happen. And like I said before, in those scenarios, the device could still be manipulating memory on those physical memory pages. So if a allocation eventually happens in the future, then you'll run into the use after free scenarios. So here's a quick example of that. We can see a DMA tag being created, an allocation happens, and then it gets mapped. And a little bit down here, You see a function is called and they check the return value. And if it failed, they will go to the fail label where they free the allocation and just return and leave, but they never actually unmapped it. So in this scenario, the device could still be manipulating the physical memory pages there. Then you have the scenarios where the unmap is driven by the device. This is where you'll see a mapping gets created, and inside the buffer are various pointers to more mapped buffers. And then the device has the ability to tamper with those pointers, and then eventually the driver would use those now modified pointers to perform the unmappings. And obviously this would allow the device to trigger just arbitrary unmaps, as well as just avoiding unmapping of the current page that they're using. So here's an example of that where we see a ring buffer get mapped, and then we see a second RES adder that gets mapped as well from the device. It gets added to the ring buffer, and later on you'll see that that RES adder pointer is what's used to perform the unmap. So that could have already been modified by the device, and that's just an arbitrary pointer that could be unmapping just anywhere else. And then you run into the unmapping too late. And this is where the developer mixes up the order of operations. So you'll see that if they decide to free the buffer and then unmap it after, there's going to be a small window where the device is able to manipulate the data before the unmapping happens, which is once again a use after free scenario. So these behaviors should be swapped. You should be performing the unmap before you free the allocation. So the conclusion with mapping issues is that if you properly exploited these, it would lead to code execution. And we thought a little bit about how you could possibly detect this at runtime. And we thought maybe monitoring the DMAR table might help, because you could see that it will keep growing. And if you don't see it getting smaller, then you know that there's some sort of mapping leak that's happening where they're just not getting unmapped. But generally, when you're writing these drivers, you want to make sure that you always unmap. The moment the mapping is no longer needed, just unmap immediately. You want to make sure that you keep your pointers cached locally and not giving them to the device so the device can manipulate them. And if you as the developer know what buffer to free, then you also know what buffer to unmap. So you should never give that behavior to the device. You should be performing that behavior yourself. Luckily, changes to the API might help here, because you can have destructors or just logic. For example, if you call unmap, it might check, or it might go ahead and free the allocation for you, or maybe when you call free, it might check, is this still mapped or not, and then perform the unmapping for you. But overall, these issues are extremely common, and it's legacy left over from when DMA was not attack surface. That's all over drivers everywhere. And then we have race conditions, and you have to remember that maps DMA buffers are essentially shared memory, so you can't trust them. Whenever you're doing any sort of data validation from the shared memory, you need to make sure that you're doing the validation after the unmapping, or after you've at least done capturing of that data, or else it could be manipulated after. And these scenarios would lead to code execution. So an example of this, we see this RX ring buffer get allocated, and then this TX ring gets set from that buffer. And down here, you see that the frag, adder, and lengths are set, and they're going through a for loop and eventually going to unmap these values. The issue is that a race condition could have happened here, where the device manipulated the adders because they're part of shared memory. So this would have been a race condition to perform arbitrary unmaps. And then information leaks. And this is kind of interesting, because before DMA was a trust boundary, you didn't really have to worry about this, because the devices could just touch memory. But now that it is a trust boundary, you have to actually care about leaking uninitialized data. And so we have 4 common cases that we've dubbed as classic, clever, race, and subtle. So the classic case would be that you allocate a buffer, you map it so the device can view it, but then you never memset it or initialized it or anything. So just very clearly, that device has access to just uninitialized data. All right, here you see straight allocation, and then it's immediately mapped. So they're missing some sort of memset or initialization of that buffer. The next one would be the clever scenario, where you allocate a buffer, but since you're a really, really clever developer, you know that that device, you only want it to write into this buffer. So since you're so clever and you want to avoid the performance hit, you're going to make it write only and not clear the memory. The issue is what happens if the device just never writes to that buffer. It might tell you that it wrote X amount of bytes, but maybe it did not write anything. So eventually that buffer is going to bubble up into whatever code is handling it, maybe in the driver, maybe in user land. And eventually you will be interpreting uninitialized data. And in scenarios where it might be a network card, for example, you might be able to have a malicious network card that's leaking uninitialized data over packets, things like that. And that will lead to obviously info leaks as well as just potential other issues because you're interpreting just uninitialized data. And here's an example of that where we see the allocation happen, and then they map it as DMA from device as write only, but they never memset the allocation. So that buffer could eventually leak. And then you have the race conditions. And this is where you would allocate the buffer, you'd map it so the device could manipulate the data, but then you memset it after it's been mapped. And what's strange is this behavior is all over the place. I think it's something that you would just assume that once you create your allocation, you would memset it. But right here, you'll see that they create the allocation, they map it, and then they memset it after it's been mapped. And we've seen hundreds of these, and I'm not sure why it's so common, but it is literally everywhere. And then you have the subtle information leaks. And this is where, let's assume you did everything right. You allocated your buffer, you cleared it, you now map it so the device can read the data, and then let's say you copy a structure to it. Well, the issue is that structure could still leak some data. Let's say there's structure padding in there that they'll see, alignment issues. There's also maybe examples where you have a char array that's 128 bytes and you only use the first 32 bytes for a device name or something, and you null terminated it, but you never actually cleared any of the memory after the null terminator. All that data would eventually get leaked to the device, which it would be able to read. And just some simple pseudocode of that, where we have a sum struct structure, and we have this unused integer within it, and we'll allocate a buffer, we map it, then we decide to fill that buffer. And the struct that we're filling it with has the elements A and B initialized, but not the unused integer. So that would leak that memory to the device. So overall conclusion, like I said, there's just tons and tons, endless piles of information leaks. This is clearly legacy leftover from when DMA wasn't an attack surface, or it's developers that are attempting to avoid a performance hit. But at the moment, you can just know that it is the norm at present time. Luckily, we think with some changes to APIs, this could be mostly solved. You would incur a performance hit, but it should solve the more obvious cases, and just only leave the more subtle cases to be looked at.
Okay, so let's talk about the elephant in the room, right? If DMA is attack surface, then now you have to go and validate stuff that you get over DMA. And that means, you know, buffer overflows, integer overflows, underflows, assignments, bugs, truncation, unvalidated length field, indexes, pointers, offsets, and so on. So here's an example of where this could go wrong. So this is a network driver that does DMA, and so it creates an allocation and maps it, and then creates that pointer to the RX desk CPU, and then it grabs a length and statistics field from it, and then it masks off some of the statistic stuff and makes sure it just captures the length, and then it does length -4. Now this means that it assumes the length is at least 4, and if you have a functioning device, that's perfectly valid. But if you have a malicious device, that you could easily give you a length of 0 or 1 or 2. And so this would trigger an underflow, and so you end up with a length that is incredibly large. And then that length is passed on to SKB put. And now we're getting into linked internals, but if you give a very large length SKB put, really, really bad things happen inside the network stack. So basically, yeah, this is totally legacy leftover from when DMA was an attack surface. Data validation is key. And I mean, you could see this like, you know, when you're parsing network protocol, you have to do validation as well, right? You have to validate lengths and indexes and so on and so forth. All of this still applies to DMA. However, things are a little bit harder because there's going to be, or there may be data in what you get back from a device that might not, you wouldn't see in a network protocol. So you could have a next or previous pointer or a physical address, something like that. And in fact, I mean, just the addresses alone might be an issue where that might be used to bypass ASLR. So another issue is where if you're sharing a data structure with your device and you end up putting some extra data in there just for bookkeeping for yourself. And the idea is that you have a portion of your data that you want a device to touch, and you have a portion of data, usually at the end, that you don't want a device to touch, but just you put it there so that life's easier for you. Because the device can now touch this stuff in the as an attack surface, that can be very problematic. And so fixing these kind of issues requires rethinking some of your data structures. And so here's an example of a driver where there's an ECB structure where all the way at the end, there's a function pointer. And then this ECB gets allocated and mapped. And then here in some interrupt handler, the ECB pointer is looked up, and this points to shared memory. And then there's a switch case that's derivative of data that comes from the device. And then it goes and grabs that function pointer, and if it's set, it calls it. Now, because this is shared memory, the device can just trample all over that function pointer, create its own function pointer, and basically redirects code execution to wherever it wants inside of the driver. And I kind of, this is again from that Thunderclap slide deck, and I wanted to put this in here because this is quite similar where this is how macOS and FreeBSD was owned with Thunderclap, where an MBUF was shared, and inside the MBUF was a free pointer. And so a device could overwrite free pointer and then go to the OS and say, or go to the driver and say, hey, I'm done with this. You know, you go handle it. And then the OS, in this case, the macOS network driver, would use that free function pointer that was overwritten by the device, which would lead to arbitrary code execution. Another interesting issue is, and this is more on the like OS platform side, but depending on how you use the IOMMU, it's possible to create a mapping that isn't just for one device, but is open to all devices. And so if you're not aware of this, or if you don't want this, and that's the default mode, then you may end up, you know, having your NIC have access to buffers that are mapped for your keyboard or your screen, and so that could lead to all sorts of leaks. And lastly, what I want to talk about is the mapping granularity of an IOMMU. So usually, most IOMMUs the granularity is about a page. We've seen some that are smaller or bigger, but generally most IOMMUs is a page big. And so if you want to go and map something that is smaller than a page, what's going to happen is it's still going to map the entire page. And so there'll be a delta like before and after that gets mapped anyway. And that'll be, you know, whatever random memory is there. And so if you end up mapping a stack buffer, then you may leak stack cookies, or you may allow overriding the instruction pointer. If it's a heap chunk that you're sharing, then you may allow overriding some heap metadata, or if you're doing it read-only, you may allow for any kind of info leaks. And in fact, in the next slide, we're going to demo an info leak in the E1000 driver in the Linux kernel. So this is, we're using QEMMU, and basically we've modified the QEMMU E1000 NIC device that goes and grabs those deltas before and after buffer. And here you see the Linux kernel booting, and you'll see that it initializes the network stack in the NIC, and then does, there you go, it does a bunch of network traffic DHCP. And so on the left, you'll see that this is our modified evil device that goes and captures those deltas before and after. And that's all initialized heap data that we're getting from the kernel. And then so we're building an SSH tunnel, and we SSH in, and we go and do, I think, an SU. And so we provide it creds. And then we go and look and we scan that memory. And our creds are in plain text inside the leak deltas. So even though you've used an IOMMU, some heap data still leaks, and in there we were able to get a plain text cred. So in this case, let me in 123 exclamation mark. This is again the similar attack to what Thunderclap did. And so, for example, in Linux, the developers have said, okay, well, if it's an external device, then we should probably have some mitigations. And so they modified the Intel IOMMU driver, which is called VTD, and they said, okay, if a device or a bridge is marked as quote unquote external, and this is taken either from the ACPI tables or from the device tree, then we create these bounds buffers, and so we make sure you don't leak stuff on like either before or after. And that more or less mitigates this particular attack. Three things to note is that if the granularity of what you want to map and the granularity of your IOMMU are exactly the same, it does not create a bounds buffer, which means you get shared memory again. And so these leak attacks that Joe talked about earlier and these races that Joe talked about earlier, those become in scope again. Secondly, in the same case, if the granularity of your allocation maps with that of the mapping, if it aligns exactly, then even if you're doing DMA from device, it does not get cleared. And lastly, if you're doing coherent allocations and maps, then bounds buffers aren't created either. In short, basically, I think we can solve a lot of these problems by having better APIs. And so what I want is basically no crazy abstractions. I want simple, clear, consistent APIs. I want APIs that allow me to query specifics of the IOMMU, such as how big the granularity is a bounds buffer going to be used? Can I map on the stack? Things like that. I also want it to give me a good API where allows me to do buffer allocations that are IOMMU aware. So that means that I know, or behind my back, it knows specific constraints, it knows the buffer alignments, it does the buffer alignments correctly, and it gives me a cleared memcedent memory. And lastly, I mean, you want good documentation for these APIs. So that, in a nutshell, is sort of the attacks that can show up in IOMMU. Our conclusion is this: using IOMMU for secure device and secure boot, and trying to protect VMs and trying to see hardware as a trust boundary, that is a large step in the right direction. Now, here's the caveat, right? It requires careful thought to be put into your implementation details. And this is at the present time in its infancy. As Joe said, I mean, those leak race conditions alone, we saw hundreds of instances. A lot of these drivers that have used DMA with their devices, they're not quite ready for prime time. There's lots and lots of sort of issues that show up. Takeaway is that simply using IOMMU for at the current time only solves trivial DMA attacks. If you want to address more advanced attacks, then you have to go fix your drivers. So that also sort of reflects in our call to action is IOMMU should be consistently applied. We need better APIs. We need more control, more transparency, more granularity, and we need better drivers. We need drivers hardened with DMA as a trust boundary. We need to find these bugs and we need to fix these bugs. Cool. Yeah, that's pretty much it.
All right. Thank you, Joseph and Ilja. We have one question, which I'll read it out for you. I think this was somewhere between the slides in the middle. Isn't it threat XOS? I think it's a comment on one of your slides, probably.
I don't know what the context is here. All of our examples, all of our code examples came from Linux and FreeBSD. It may have been that some of these also are in ThreadX. I don't know about that.
All right. Friends, do you have any questions to ask to our speakers? Please send them via the Zoom chat. Maybe you must have received some directly in private. Could you check your Zoom chat as well?
I'm not seeing. Oh, okay, there's one. Are there some standards like secure coding to develop drivers that would help developers of drivers to attack surface? That's a great question. At the present time, I'm not aware of this. There are, as Joe mentioned earlier, there are some general guidelines in the Linux documentation about which direction to use. But beyond that, we haven't seen this yet. This hasn't really occurred to me, but this is a really good note. Yeah, we should do this. We should update documentation. We should update manuals. We should update books. Where if you talk about drivers, it should say if you're concerned about DMA or IOMMU and DMA is a trust boundary, then you should watch out for these issues. And then the other question is, how many drivers did we find issues on? I don't know, Joe. Lots and lots and lots. It's hard to put a number on it. I mean, it's to the point where you grep for APIs and it's like, oh, there's a bug and there's a bug and there's a bug and there's a bug. Almost all, I don't see. There's so many drivers in Linux kernel that there's no way we got through all of them. But just through grepping, it's just, I mean, it's easily hundreds, probably thousands.
Okay, then thank you, Ilja and Joe, for this amazing session.